Hi everyone. In this video I will be going through the final exam from spring 2018, and that will be the final review session for the upcoming Chem 115 final exam. That exam is going to be from 9 a.m. on Wednesday, May 6th, and that'll go until 9 a.m. the following day, so you'll have that 24-hour window to complete your exam. You'll have 2 hours to work on the exam, so 2 hours anytime within that window. So if you want your full 2 hours, make sure you start before 7 a.m. on the 7th, because the exam will close at 9 a.m. So to get your full 2 hours, you'll need to start before 7 a.m. on Thursday the 7th. There will be 30 questions, and they are going to be multiple choice. It'll be similar to what you saw on exam 3, which was also on Blackboard. So, starting here at number 1, it says identify the proper isotope and element X present in the nuclear fission reaction equation shown below. So we have X there, and we need to identify what element that is based on the other factors that were given in the equation here. So the way that I typically do this is just add up the mass numbers on one side. So the upper number is the mass number and the bottom number is the proton number. So I add up the mass numbers, 2, 3, 5 plus 1, and then add up the proton numbers, 92 plus 0. So that is 236 over 92. And then do the same on the other side. So 94 plus 1 times 4, because there's 4 neutrons, each of which have 1 mass unit. So 94 plus 4. And then 39 plus 0. So that's 98 over 39. And then since we want to solve for A and Z and then get X from that information, we'll subtract the numbers on the product side from the numbers on the reactant side. So that's going to be 236 minus 98 and 92 minus 39. That is going to give us 138 and 53. We see that 138 over 53 matches with one of these elements here, and that is A, iodine. Iodine 138 has 53 protons, so our answer for problem 1 is A. Number 2 asks which is the full ground state electron configuration for a bromine atom. So these two things are important here. It has to be the full configuration, it has to be the ground state configuration. So we can eliminate a couple of these automatically. A and C are not the full configuration. They have a noble gas condensing part of the electron configuration, so we can eliminate those immediately. If you also look at the rest of them, you can see here that E goes 1, 2, 2, 3, 3, 3, 4, 4. That's not how an electron configuration is written. It starts with 1, 2, 2, 3, then 4, 3p, 4s comes before 3d. So this one is just written in increasing numerical order. So we can eliminate that one as well. So that leaves us to decide between D and B here. But we also want the ground state, so there aren't going to be any electrons in higher orbitals than they should be in, which is what we see here. So instead of 3d 10, we have 3d 9, and that 10th electron has been moved over into the p orbital here. Whereas for B, we do have 3d 10, 4p5, and if we look at our periodic table, we see that bromine is in this second to last row of the p block here, so it would have 1, 2, 3, 4, 5 electrons in its p shell, which is what we see here. You can also count the total number of electrons. These two do have the same number. They each have 35 electrons, but B matches with the full ground state configuration, so that's the configuration for a bromine atom. Number 3, use the Rydberg equation to calculate the wavelength in meters of the photon absorbed when the electron in a hydrogen atom undergoes a transition from n equals 2 to n equals 7. So for that, we can look at our equation sheet, find the Rydberg equation, which is here, and we'll also need the Rydberg constant for this problem. So the Rydberg equation, I'll just write out at the top here. So the wavelength that we're looking for is going to be this lambda. R will be the Rydberg constant. N1 is going to be 2, and N2 is going to be 7, because we're going from 2 to 7, and then we're going to take the inverse of each of those squares and then subtract them from one another. So if we fill in first this parentheses part, we'll have 1 over 2 squared minus 1 over 7 squared. So that'll be 1 over 4 minus 1 over 49. So rewriting that in the equation, that'll give us 0.25 minus 0.020408. So then we can add in our Rydberg constant, 1.096776 times 10 to the 7th, and that is inverse meters. We'll multiply that times the difference of those two, 0.229592. So when we do that, we get that 1 over lambda is equal to 2.51811 times 10 to the 6th inverse meters. So we have 1 over lambda equal to 2.51811 times 10 to the 6th inverse meters. So if we take the inverse of both sides, so dividing 1 by this number and dividing this side by 1 as well. So 1 over lambda is equal to 1 over the right side of the equation. So that'll give us lambda is equal to 3.969 times 10 to the negative 7th meters. So we see that that matches with C. So C, 3.969 times 10 to the negative 6 meters, is going to be the wavelength of the photon that we get when an electron undergoes that 2 to 7 transition for hydrogen. Number 4 asks what percentage of original carbon-14 remains in the heartwood of a bristlecone pine that is 3.5 times 10 to the 3rd years old. The half-life of carbon is 5.73 times 10 to the 3rd years. So for this, we will use our decay equation here. So that equation is ln of n over n0 is equal to negative kt. So first we'll want to solve for k using our half-life of carbon. So to do that, we will take the ln of 1/2, if we want to solve for a half-life, is equal to negative k times 5,730. The ln of 1/2 is given to you here on the equation sheet, 0.693. That is equal to negative k times 5,730. So this is negative 0.693. So there, 693 equals k when you divide each side. So that gives us that our k value is equal to 0.00012094. So we're going to use that and plug that back into our equation when we want to solve for n here. N is the number of amount of carbon that remains, and 0 is the amount of carbon that we started with. So we'll want to solve for this n. We know k, we know t, we know n0. So to solve for that n, we'll need to take each side to the e. So we'll raise this side to e, and this side as well. So the e power of the natural logarithm will cancel. So we'll get that n over n0 is equal to e to the negative kt. We know what k is, we know what t is, and we also know that n is equal to 100, let's say, just as make our percentage calculation easier. So we have n over n0 is equal to e to the negative kt, so we know that k is 0.000120094 times t, which is the half-life. We get that e raised to the power of negative 0.42329. So when we raise e to that power, we get that n over n0 is equal to 0.654888, and so on. So when we set n0 equal to 100, it could be any arbitrary number, but to make our percentage calculation easier, we find that 65.48 is the percentage of carbon-14 that remains. So that matches here with answer choice D, 65.48%. Number 5, what are the coefficients in the following unbalanced chemical equations shown below? So for these types of balancing problems, I usually start with one atom that's typically carbon, and then move on and balance the other atoms from there. So if on this side we have 6 carbons in this hexane molecule, we need to have 6 carbons over here. So let's give this a coefficient of 6. So here we'll have 6 carbons, here we'll have 6 carbons, but 6 times O2, carbon, will also give us 12 oxygens. So then if we want to balance the amount of hydrogens, we see that we have 14 hydrogens here, we have an H2O here. So we can take this side by 7, so that'll give us 14 hydrogens, and remember it'll also give us 7 oxygens. That will give us, match with our 14 hydrogens that we have here in hexane. So then we need to balance the oxygens. That's the remaining atom that we have not yet balanced. So here we have 12 oxygens and 7 oxygens. So that's a total of 19 oxygens that we have here. In order to get 19 oxygens, we need to multiply this by 9.5. So if we multiply that by 9.5, we do get 19, and this is oxygen. So our coefficients temporarily will be 1, 9.5, 6, and 7, but we can't have a fractional coefficient. So we'll take each of those coefficients, multiply them by 2, so that'll be 2, that'll be 19, 12, and 14, so those will be the coefficients for each of these reactants and products in this equation, and we see that that matches with answer choice E here, 2, 19, 12, and 14, so the answer there is E. Number 6, which ion in the isoelectronic series shown below has the largest radius? And it says atoms in an isoelectronic series have the same electron configuration, which means that they have the same number of electrons, but they don't necessarily have the same number of protons. As we can see, calcium has the most protons because it has the highest charge, highest positive charge. Sulfur has the least amount of protons because it has the most negative charge. And if they each have the same number of electrons, that would stand to reason that calcium has the most protons. And if we consult our periodic table, we see that sulfur has 16 protons and calcium has 20 protons, so that matches up. And typically in an isoelectronic series, as you go to the elements with more protons, so this will be our proton number, this will be our electron number. They all have the same number of electrons, but sulfur has 16 protons, chlorine has 17 protons, argon is neutral, so it has 18 protons and 18 electrons, so that means the rest of our species here will also have 18 electrons. Potassium has 19 protons, 18 electrons, and calcium 2+ has 20 protons and 18 electrons. So as you keep the same number of electrons but increase the amount of protons, that greater positive charge, let's say this represents sulfur, the lesser positive charge here is not going to be able to hold the electrons as tightly as this increased amount of positive charge holding the same amount of electrons. These are just representative, but the increased positive charge is going to hold the same number of electrons more tightly when you have a greater number of protons. So calcium would have the smallest radius. That would mean that sulfur has the largest radius because the 16 protons are least able to hold those 18 electrons. So here the largest radius will be sulfur 2-. Number 7, oxygen has a lower first ionization energy than nitrogen because we need to pick one of these here. So there's a few that we can eliminate pretty quickly that don't have anything to do with ionization energy. C, liquid nitrogen is colorless, liquid oxygen is blue. That doesn't have anything to do with ionization energy. Also, B, O2 contains only a double bond, whereas N2 contains a triple bond. That doesn't have anything to do with ionization energy either, and neither does D. The fact that the 2s orbital may or may not be shielded by the 2p orbital does not affect the ionization energy of oxygen. So we need to check and see that A removing the paired electron and ionizing oxygen gives a half-filled p orbital is correct, or if the statement is false. So if we look at the 2p electrons of oxygen, so these represent the 2p orbital, and then oxygen being the 1, 2, 3, 4th atom in that p orbital, it'll have 1, 2, 3, 4 2p electrons. So this is oxygen. So if we look at our nitrogen 2p orbital, nitrogen is the 3rd atom in the p shell, so it'll have 1, 2, 3 electrons like that. So nitrogen 2p orbital is currently half filled. Oxygen has 1 completely filled and 2 half filled. So if we remove, so we'll take away 1 electron from each side. Let me redraw what that looks like. So taking away 1 will now give oxygen a half-filled shell, but nitrogen will lose its half-filled shell. So that would mean that oxygen is more readily able to lose an electron, because losing an electron actually gives it the half-filled configuration, which is stable, compared to 1 too many or 1 too few electrons. So when you take 1 away from nitrogen, you are breaking the half-filled configuration. So that would lead me to believe that oxygen is easier to ionize than nitrogen. So if we look at A, removing the paired electron and ionizing oxygen gives half-filled p orbital. That is true, and that is the reason that oxygen has a lower first ionization energy than nitrogen. So the answer for 7 is A. Moving to number 8, which element below has the most metallic character? So if you remember the trends, a metallic character increases as you go this way across the periodic table. So from right to left, and it also increases as you go down. So down the row, if we look at our elements here, see that we have fluorine, bromine, gallium, cesium, potassium. Fluorine is way up here, so then as we go down to bromine, we're slightly increasing the metallic character. We'll go right to gallium, or left to gallium, increasing the metallic character more. We're now actually where gallium is a metal, whereas bromine and fluorine are not metals. So from gallium, we'll move over to potassium. So we've increased the metallic character quite a bit in that move from gallium to calcium. But then we see we have cesium, and if we go down to cesium, that is going to be the most metallic because it is furthest down here. So fluorine, bromine, gallium, potassium, and then where I've marked the X here is cesium. So if we follow our trend, these elements all follow that trend. So the most metallic here is going to be B, and that is cesium. Moving to number 9, which of the following has the highest third ionization energy? So in any particular ionization energy here, the third is high. That means that you are removing an electron from a closed shell. So for this case, the third is high, so that would mean that there are 2 electrons in the valence shell. So you can tell which elements have 2 electrons in their valence shell by looking at the periodic table. The A groupings here, so 1A, 2A, 3A, 4A, 5A, and so on. Those are how many valence electrons we have. So if we look at our periodic table, in the second row we have lithium, beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, and neon. So 3, 4, 5, 6, 7, and 8. We want something with a high third ionization energy, which means it has 2 valence electrons. So that is going to be beryllium. When you take away 1 electron, you get beryllium 1 plus. When you take away a second electron, you get beryllium 2 plus. And then you try to take away that third electron, you're now breaking the closed shell configuration, which is what you have in this noble gas row. So beryllium is the answer here. It has the highest third ionization energy. If you look at the other choices, boron, carbon, nitrogen, and fluorine, these over here, you can take away 3 electrons from boron, carbon, nitrogen, or fluorine and still be within this 1p or 2s row here. So the answer for 9 is beryllium. Moving to number 10, says using the data below, calculate the lattice energy of potassium bromide. So here we have the overall equation. We're going from solid potassium bromide to gaseous potassium and bromine ions. We're given each of the chemical reactions here, the type of reaction, and the heat in kilojoules per mole. So if you remember the reaction equation for lattice energy calculation, the energy of the lattice is equal to negative delta HF, which is the heat of formation, plus H1, H2, H3, and H4. So these are in no particular order. H1, H2, H3, and H4. The only one where the label matters of these is the heat of formation. That goes first and is negative. We also see that it has a negative sign here. So when we plug these numbers into this equation, we should get the lattice energy, taking into account that we only require half of a BR2. So anywhere that we see a BR2, we're going to need to divide that energy value by 2 to get the energy for a single bromine atom. So for the electron affinity, it's just a single Br, so we don't need to divide that number. But for the bond dissociation energy, you're dividing Br2 into 2 bromine atoms. That is where we need to divide that value by half. So if we take that the energy of the lattice is equal to the negative heat of formation, we are going to add 90, then 420, and then for the bond dissociation energy, we'll divide that by 2. It's 1/2 times 190, and then add the electron affinity. So that is also a negative number. If we solve for 190 divided by 2, we get that that is 95. So the negative of this negative is positive, so 395 plus 90 plus 420 plus 95 minus 325 is going to give us the lattice energy, and that is equal to 675. So the energy of the lattice is 675. These were all in kilojoules per mole, so this is as well. We see that that matches with answer choice D here. So that is the energy for the lattice of potassium bromide. Number 11, what is the molecular formula for the following skeletal structure? So we are given this structure here. So for these, I like to just redraw it with all the carbons and hydrogens. So carbon double bonded to carbon, triple bond. Remember that there are carbons at each of the ends of that triple bond there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And that's what we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to have C9, so we can eliminate then B, C, and E, leaving us with A and D. So this structure is going to either have 14 or 13 hydrogen atoms, and we can decide that just by filling in the bonds on carbon so that each carbon has 4 bonds with hydrogens. So here carbon has 2 bonds, so each of those remaining 2 will be to a hydrogen. This carbon has 3, so it'll have 1 bond to hydrogen. Each of these already have 4 bonds. This carbon will add 2 bonds. This carbon has 4 bonds, and then to each of these 3 we will add 3 hydrogens, since each currently has just a single bond to this carbon here. So if we count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So H14, that matches with answer choice A, C9H14. So that is the skeletal structure for the formula for the given skeletal structure here. So number 12 asks, how many sigma and pi bonds are in the molecule shown in question 11? So that is this molecule that we have here. So we can look at that while we try to decide the sigma and pi bonds. So pi bonds, remember, are any place that you have a multiple bond, you're going to have a pi bond. So double bonds will have 1 pi bond, triple bonds will have 2 pi bonds, because any bond above a single will be a pi bond. So we see we have 1 pi bond there from this double bond, and 2 pi bonds in our triple bond. So we're going to have 3 pi bonds, so we can therefore eliminate A and D. Those each do not have 3 pi bonds. Then we can count up the remaining sigma bonds, which are going to be any place there's a single bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. So there should be 22 sigma bonds. That matches with answer choice E here. 22 sigma bonds, which is what we calculated from our structure, and 3 bonds, which is also what we counted as well. So those both match. So our answer here is E, 22 sigma and 3 pi bonds. Moving to number 13, which of the following molecules has the most lone pairs in its Lewis structure? So probably the simplest way to determine that would just be to quickly draw each of the Lewis structures. So SiH4, silicon there is the central atom with 4 hydrogens around it. Bf3, boron is central with 3 fluorines, and each of the fluorines will have 3 lone pairs. So we want the structure with the most lone pairs, so this is going to be a good candidate for that because it has 3 fluorines. NH3, nitrogen central with 3 hydrogens, and then nitrogen also has a lone pair. C2H4, the 2 carbons will be central, and then to give each carbon its 4th bond, we'll make that a double bond in the middle. There are no lone pairs in that structure. C2H2 is similar. The two carbons will be central with one hydrogen on each, and then we'll make that middle bond a triple bond so that each carbon has 4 bonds there as well. Again, no lone pairs. So in the BF3, each fluorine has 3 lone pairs, so 3 times 3 is 9 lone pairs. Here, nitrogen has a single lone pair, so most lone pairs is going to be B, that is BF3. Which choice correctly identifies a molecule that can hydrogen bond with itself in the left column here, and a pair of molecules that can hydrogen bond with each other in the right-hand column. So remember, for hydrogen bonding, there needs to be either an NH, OH, or FH bond in order for there to be hydrogen bonding. We see that there's only one molecule that has that. 4 here has an NH2 group, so it has 2 NH bonds, so 4 can hydrogen bond with itself. So that means that our answer will either be D or E. We can eliminate A, B, and C because 4 is the only one that can hydrogen bond with itself. And then we need to look at which molecules 4 can hydrogen bond with. So hydrogen bonding can happen when you have either of these 3 atoms. They can act as acceptors. These are the donors. They are what donating the hydrogen bond here, and these can act as acceptors. So there's only one other of these molecules that has a nitrogen, oxygen, or fluorine. That is 1. So 4 and 1 pairing is what we have for answer choice E. That is going to be the answer to 14. 4 can hydrogen bond with itself because of the NH bonds, and 4 can also hydrogen bond with acetone here because it has an oxygen atom. So 14 is E. Number 15, which of the structures shown is a reasonable monomer for addition polymerization? So the 2 types are addition polymerization, condensation polymerization. So remember, in addition polymerization, you typically have an alkene, which adds to a neighboring alkene to form the polymer backbone. Condensation, you're condensing out some small molecule, so typically you would have something like a carboxylic acid on one end and an OH on the other end, or an NH, and then when you combine those two, you get now this oxygen bonding to this carbon. You kick out this small molecule, such as water. So that's an example of condensation. So of those 2, B is the only one which has an alkene. Therefore, it's the only one that can form an addition polymer, which does not change the formula of the monomer unit, whereas when you form a condensation polymer, you're losing a small molecule, something like water or HCl, something like that. So 15 here is going to be B. This ethene is going to be a reasonable monomer for addition polymerization. Also, if you know that this is ethene or ethylene, polyethylene is a type of plastic that's pretty common, so that's another way you could potentially think about that if you know that that is ethylene. Number 16, which of the following molecules contains an ester functional group? So an ester is similar to a carboxylic acid. So here you have an R group, so that'll represent a carbon connected to a C double bond O, and then that carbon will be connected on the other side to an oxygen, and then that oxygen will be connected to another carbon. So R groups typically just represent some sort of a carbon chain. So we're looking for this type of formula. A, B, and D all have carbon double bonded to oxygens, which is required. And then we're looking for an oxygen also connected to the carbon of that CO double bond. D is the only one that has that. That structure matches pretty well with our general formula that we've drawn here. So A is an aldehyde and B is a ketone. So D is the answer. That is our ester functional group. Number 17, if the average molar mass of a polymer is 5.50 times 10 to the 4th grams per mole, and the average number of repeat units in each polymer chain is 550, which of the following is the most reasonable choice for the monomer that was used to make the polymer? So we know the average mass, we know the number of repeating units. So if we divide the average mass, so 55,000 divided by 550, that's going to give us the mass per unit, so that will be equal to 100. So we're looking for a monomer that weighs 100 grams per mole. So if we calculate using our periodic table here the molecular mass of each of these monomers, there's going to be 12 for each carbon, 1 for each hydrogen, roughly speaking. So I'll calculate some approximate values for each of these just so we can get an idea if there's some we can eliminate. So 2 carbons is 24, 4 hydrogens is 4, so that'll give us about a molecular mass of 28 there. Here again we have 2 carbons and 1 oxygen, so 24 plus 16 is 40, and then we have 4 hydrogens, so that'll give us 44. So here we have 2 carbons, so 24, and then we have 1, 2, 3, 4 fluorines. Fluorine's molecular weight is about 19, so 19 times 4, so that's going to be 38 times 2 is going to be 76, so 76 plus 24 is 100, so that does match with our calculated molecular weight here. But then if we calculate the final one, just for completion, it would be 24. And then chlorine each weighs about 35.5, so that'll be 70.1, 140.2, so that'll be about 166. So that's going to be too much. A and B will be too light, but C will be just right. So this 4-fluorine ethylene tetrafluoroethene weighs 100. That is going to be the reasonable choice for the monomer that was used to make the polymer, where the average mass of the polymer is 5.5 times 10 to the 4th with 550 repeat chains. So 18, pick the answer that best completes the following statements. SO3 has a blank molecular geometry. When it gains 2 electrons, it has a blank geometry and is blank. So we're given some options here. So it looks like it's going to either be trigonal pyramidal or trigonal planar for the first one, the same 2 options for the second, and either polar or nonpolar for our final option here. So if we look at SO3, there's 1 sulfur, 3 oxygens, so it's likely that sulfur is going to be our central atom. If we have oxygen and sulfur, we see that they each have the same number of valence electrons. They each have 6, which makes sense. They're both in the 6A column. So we'll draw 6 around sulfur, and we have 3 oxygens, each with 6. So for each oxygen, we need 2 additional electrons to give each of those a complete shell. And the same for sulfur, we need additional electrons there as well. So if we donate 2 electrons from sulfur to oxygen to make oxygen have a complete shell, that will look like this. So say we take this one, match it up with that one, this one, match it up with that one, do the same here. Sulfur is capable of expanding its shell, whereas oxygen is not. So if we form a double bond between sulfur and each of the oxygens, which is what we drew here, so now each oxygen has its closed shell. Sulfur has an expanded shell because if it has 2, 4, 6, 8, 10, 12 electrons, that's more than 8, but sulfur is one of the elements that can expand its shell. So sulfur with 3 oxygens, that's going to be 3 electron groups. So when you have 3 electron groups, those are going to be trigonal planar. So that's what we'll have here, trig planar. So that means that our answer will either be B or D as the first option for A and C is trigonal pyramidal. That is not what we have. So then we need to choose what the next one will be, which is either trigonal planar or trigonal pyramidal when it gains 2 electrons. So if we redraw our SO3 here, we'll give it 2 additional electrons on the sulfur because it can expand its shell and oxygen cannot. So now we have 4 electron groups. So when you have 4 electron groups, that is when you have a trigonal pyramidal electron geometry. So we're looking for pyramidal for the second option. That is going to be here. So that would mean that our answer is D. That would indicate that this molecule is polar as well. When you have the sulfur and oxygen double bonds all in the plane, the individual bond dipoles all cancel one another, but when they're out of the plane like this, which is caused when you add that additional lone pair, now you have the same bond dipoles, but the vertical component doesn't cancel, only the horizontal component still cancels, so you do have an overall molecular dipole as well, which matches with D also. So for 18, our answer is D. Moving to problem 19. Absorbance values for 5 standard solutions were determined at 410 nanometers with a 1 centimeter path length. The calibration standard curve is shown below, so that's what we have here. The absorbance of a solution of unknown concentration containing the same solute was 0.623. Calculate the concentration in molar of the unknown solution. So we have absorbance on the y-axis, concentration on the x-axis. So we know that the absorbance is 0.623, so that's going to be somewhere along our y-axis here. So 0.623 is going to be approximately a quarter of the way between 0.6 and 0.7. So that's going to lead us over here where it intersects with the calibration curve there. So that's going to be, let's say that's 0.9. It's going to be somewhere between 0.9 and 1, but we see that there are 2 options that fit that criteria, so this is just a way of getting a rough estimate of where the concentration might be. So between 0.9 and 1. to get the exact value, we can plug our absorbance into our calibration curve here as y. So 0.623 will then be equal to 0.6491x plus 0.0053. We'll subtract 0.0053 from 0.623 and then divide that by 6491 in order to solve for x. So that will give us 0.9516. So that matches, once we round, with choice B here. So the concentration of the solution with the 0.623 absorbance is 0.952 molar. That matches about with what we saw here of roughly what our concentration was. So the answer for 19 is B. So for number 20, calculate the yield of alum if you start the experiment with 0.42 grams of aluminum and end with 6.04 grams of wet alum with the formula. The equation for the synthesis of alum is shown below. So here is our starting material, and here is our product alum. So for every aluminum, you get 1 potassium aluminum hydroxide, because the coefficients are 2 and 2 for each of those. So for 1 aluminum, you get 1 potassium aluminum hydroxide. So there's the stoichiometry of the starting material to the product that we're concerned with here, because it's the one that's carried over into the next equation. The stoichiometry there is 1 to 1. So when you add aluminum, you get potassium aluminum hydroxide. That's what's put into the next equation. So effectively, this whole first equation can take the place here of this potassium aluminum hydroxide. So we look at the coefficients then of the potassium aluminum hydroxide, which is 1. The coefficient of alum is 1. So the stoichiometry there is also 1 to 1. So for every mole of aluminum we put in, we should get 1 mole of alum, because there's a 1 to 1 stoichiometry from the starting material to our product alum here. So we're given that we start the experiment with 0.42 grams of aluminum. We can calculate the number of moles of aluminum by dividing that by aluminum's molar mass, which we can get from our periodic table, 26.98 grams per mole. When we divide those two, we get 0.015567 moles. So we start with that many moles. If we get 100% yield, we should get that many moles of alum back. So we need to calculate the molecular mass of alum. So if we have potassium, and I'm just getting each of these values from the provided periodic table, 39.1 for potassium plus 26.98 for aluminum. Then we have SO4 2, so the whole SO4 unit will be multiplied by 2. So that'll be plus sulfur, which is 32.07, plus 16 for oxygen, times 4, and then that whole thing will be times 2. So that'll be for the KAl SO42 portion. We'll add that to the 12 H2Os. So we have, again, 16 for oxygen. We'll add that to 1.008 for hydrogen, and there are going to be 2 hydrogens per water. So that whole thing, the whole water unit, will be multiplied by 12. So when we do that math, we'll add the portion for the alum, we'll add the portion for the hydrate. That'll give us a molar mass of 474.412 grams per mole. That's the molar mass of potassium alum dodecahydrate here. So if we multiply the amount of moles, that would give us 100% of our alum. So the moles of the starting material, aluminum, times the molar mass of the product will give us the theoretical yield. So what we would get if we got 100% yield from the reaction, that gives us 7.38517 grams. So that would be theoretical, and we're given that we have 6.04 grams of alum product that we actually got from the reaction. So the actual yield over the theoretical yield will give us the percent yield. So 6.04 divided by 7.38517 is equal to 0.8178. Multiply that by 100 will give us 81.78%. So if we round that, that'll give us 82, which matches with answer choice A there. Moving to number 21, creating the organic compound luminol is a two-step process and requires isolating luminol and the intermediate. What laboratory technique was used to isolate the two compounds? So we're looking for a technique here. So separating funnel, we can eliminate. Separating funnel is not a technique, that is a piece of laboratory equipment. So we have to decide between filtration, heating, and crystallization. So one of these is typically used to separate things. That would be filtration. Heating, you're not going to be separating anything typically during heating alone. You can use heating to accomplish other things, but here we just have heating. So just heating something isn't going to necessarily separate anything. And crystallization could potentially be used for separation, but it's typically used just as a purification method of one compound. So that one is likely out as well. If you think back to the luminol lab, you did use this, not the separating funnel, you used the Buchner funnel. So that little guy where you put your filter paper in here, you then attached that to your filter flask. Remember the one with the little sidearm? You hooked that up to your aspirator, and then you pulled your solution through here. So your solution comes out. You collect the luminol on the top. The stuff you don't want gets filtered out to the bottom. So that is a type of filtration. So A is the answer to number 21. Filtration is what you used to separate both the luminol and the intermediate from the surrounding impurities. Number 22, shown below is a portion of the nutrition information for baked Ruffles potato chips. In lab, a student treated 7.25 grams of these chips with 25 milliliters of isopropanol. After filtering and evaporating off the isopropanol, the student got 0.325 grams of fat. Based on the nutrition information, what was the percent recovery of this extraction? So first we need to find out the percentage of a serving that was used. So a serving size is 1 ounce. Given that that's 28 grams here, they treated 7.25 grams of the chips. So our fraction of a serving will be 7.25 over 28. That gives us 0.2589. We then need to determine the percentage of fat that could have potentially been present in that portion based on the percentage of the serving that we used. So we're given here that the total fat should be 3 grams. So 3 grams multiplied by the portion of the serving size. That will give us that we could potentially have 0.7767 grams of fat in this 7.25 gram sample of potato chips. The amount of isopropanol here isn't really important, but we're given that the amount of fat that was recovered was 0.325 grams. Similar to the alum problem, you put the actual yield over our theoretical yield. That is going to give us the percent recovery, which is what we're looking for of the extraction. So that will be 0.4184. We multiply that times 100 to get our percentage. That is equal to 41.8%. It's pretty close to B here. Maybe if I rounded more or less, we would have got 41.7, but that's the only one that's even remotely close to the answer that we calculated. So B, 41.7%, is going to be our answer for number 22. 23. Which of the levels of protein structure is associated with the overall shape and structure of a protein complex containing multiple polypeptide chains, such as the potassium ion channel? So the potassium ion channel was something that was discussed in the biomolecules lectures. The key words being here, multiple polypeptide chains. So multiple polypeptide chains would indicate that you have multiple units of varying proteins, or likely multiple units of the same protein. So you could have 3 similar proteins all coming together to form one larger protein complex, for example, that we see here. So each of these could represent a different polypeptide chain. And when you have something like that, that represents quaternary structure. So just to give a rundown of the rest, primary is just your chain of amino acids with no additional structure, just listing what amino acids you have. Secondary is when that string of amino acids starts to form into secondary structures, things like alpha helix or beta sheet. Those types of things are secondary structures. Tertiary structures is when you have the 3-dimensional shape of the entire protein, incorporating things like helices and sheets. So here you might have a helix as part of your protein with then like a little loop, and you have, let's say, a beta sheet that goes back and forth with another loop here, and then maybe another alpha helix, something like that, where you have the full 3-dimensional structure. This would be one protein unit. That is something that is represented by tertiary protein structure. Then when you have multiple of these, let's say this represents our triangle here, so you have 3 of these tertiary structures to make a larger structure. That's when you have quaternary protein structure. So our answer here is D. Quaternary is not really a thing that exists, so you don't need to worry about that one too much. 4. Which of the levels of protein structure results from the intermolecular forces between amino acid side chains? So here you have that there are intermolecular forces between the side chains. So as we saw on a previous question here, primary is just our amino acids. So that one is out. Quaternary, we said, doesn't exist. Secondary was things like the alpha helix. Tertiary was the overall larger structure of our protein. This is just the simple little protein, made up protein that I drew here, so that would be represented by tertiary. And quaternary was when I said you had multiple of some sort of a tertiary unit. So quaternary we can pretty much rule out. Those are not combined as the result of intermolecular forces between the side chains. So between secondary and tertiary, if you remember what forms the alpha helice and beta sheet, those are actually intermolecular forces between the backbones of the amino acids, where you have hydrogen bonding between the backbone, so the side chain is going to be here, so there would be a side chain there, there'd be a side chain here. So what's actually holding these two strands together to form a helix or a sheet is going to be intermolecular forces, but they're not between the side chains, they're actually between the backbones. So we can eliminate B, which leaves us with C as our answer. Tertiary protein structure results from the intermolecular forces between the amino acid side chains. Number 25. Which of the following statements about DNA is false? T pairs with A bases. That is true. A and T do pair together. The DNA structure includes carbohydrates. That is also true. So it's DNA. Deoxyribo. So ribo is for ribose, which is included in DNA, so that is correct. G pairs with C bases. That is also correct. If A pairs with T, it would make sense that G pairs with C. DNA base pairs bases pair based on hydrogen bonding interactions. That is true. When you have A and T, they have hydrogen bonds between the base pairs. That's what keeps the base pairs together. These are not drawn accurately, just to give you an idea. So that is true. E, phosphate groups form the center of the helix, bases are on the outside. That one is false. Bases form the center of the helix, so you would have your phosphate, your sugar, your base, like that. Then you'd have your hydrogen bonds between your bases to the pair base, which would be connected to the backbone on the opposite side. So the phosphates are not in the center of the helix. They are on the outside. The bases are on the inside, not the outside. So number 25, the answer is going to be E. Looking at number 26, what are the hybridization and ideal bond angles around the indicated oxygen? So oxygen here has two bonds to the adjacent carbons. Remember that it also has two lone pairs. So there's 4 electron groups around oxygen, when you have 4 groups, you're going to need 4 orbitals to accommodate each of those electron groups. So typically it would be sp3. There's 4 sp3 orbitals. When you combine 3 p orbitals and 1 s orbital, you get 4 sp3 orbitals. 1 plus 3 is equal to 4. So you need 4 orbitals when you have 4 electron groups. So sp would be out, sp2 would be out, so leaving us with either D or E. Those are the only choices that have 4 sp3 orbitals to accommodate our 4 electron groups around oxygen, 2 bonding groups, and 2 lone pairs. So when you have 4 groups, that is when you have the 109.5 degree bond angle. 3 groups would give you 120. 2 groups would be 180. So there's your central atom. Your 2 groups would be directly opposite. 3 groups, they're arranged in a triangle with 120 degrees in between. When you have 4, that's when you have a tetrahedral arrangement and 109.5 degree bond angles. So E here is going to be the correct answer. It has sp3 hybridization and 109.5 degree bond angles. Alright, moving to number 27. What is the pH of deionized water after sitting in a standard room atmosphere for a few minutes? So remember that when you have pH 1, that is going to be acidic, all the way up to pH 14, which is going to be very basic. So the pH of water is about 7-ish naturally, so about halfway in between extremely acidic and extremely basic. So when it is sitting in the room for a few minutes, which of these will be the case? So if you dissolve oxygen in water, which is possible, there's nothing that would make it have a pH of 1. If we look at B, it's slightly acidic from its neutral, 7.0-ish. There is something that could cause it to become slightly acidic. If you have water and you mix a little bit of carbon dioxide into there, which would happen if it was sitting open in the air, you actually get something that is called carbonic acid. So your H2O and CO2 combine to form carbonic acid. So this is somewhat acidic. So B is likely the correct answer. We'll just go through the rest here real quick. 7, due to autoionization of H2O. Even if it were to ionize, that wouldn't necessarily change the pH. 7.4, slightly basic, but there's nothing that would cause it to have any osmotic pressure. There's no barrier between the water and something else. And 10.0, quite basic due to boiling point elevation. Boiling point elevation shouldn't have any effect on the acidity or basicity of the water, so B here is our answer. It's become slightly acidic due to dissolved CO2. When you dissolve the CO2 in the water, you get your carbonic acid, which does cause the water to become somewhat acidic. Which of the following is the strongest electrolyte? So here we have a couple of electrolytes. The strongest is going to give us the most ions when you dissolve it in water. So when you dissolve acetic acid in water, you will get that, and that. So there's 2. When you dissolve LiNO3, you'll get the Li plus and NO3 minus. So there will be 2 as well. Glucose is a non-electrolyte, so you'll get 1 ion. Carbon tetrachloride is also a non-electrolyte. Despite it having chlorines, they are covalently bonded to the carbon, so they will give you 1. And MgCl2, there you would get Mg2 plus and 2 Cl minuses, so there you have 3 ions. So the strongest electrolyte here would be E, MgCl2. Moving to 29, which of the following is not an example of a colligative property? So a colligative property changes based on the number of ions present in the molecular formula for a given molecule. So things that we know for sure, things like boiling point elevation is a colligative property. Freezing point depression is a colligative property. If you dissolve sodium chloride in water, its freezing point will decrease, its boiling point will also increase. That will also decrease vapor pressure. If you put NaCl, sodium chloride, in some water, the vapor pressure of the water will decrease. It'll also increase the osmotic pressure. So the only one here that is not a colligative property is going to be molar mass. The molar mass does not change based on how many ions a formula may break down into. Which of the solutions below would you expect to have the lowest freezing point? That's question 30. So there are going to be 2 factors here that affect the freezing point of a given solution when you dissolve these things in there, and that is going to be the Van Hoff factor, so that would be I, and the molality, lowercase m. So if we make a table with the molality and the Van Hoff factor, the molalities are given to us here. So 1, 2, 2, 1, and 2.5 are the molalities of each of those solutions. And those are just the numbers that were given with the lowercase m. And the Van Hoff factor is roughly how many ions a given solute will break into when you dissolve it into water. So calcium chloride will have 3. Methanol is a non-electrolyte, so it will have 1. Sodium hydroxide will break into sodium and hydroxide, so there will be 2. Sodium hydroxide again, and methanol, we said, was a non-electrolyte. So when you multiply m times I, that will give us 3, 2, 4, 2, and 2.5. So the choice with the greatest combination of molality and Van Hoff factor is going to be 2 molar sodium hydroxide. That is our answer. That will have the lowest freezing point of these solutions that we see here. Number 31, on the solution handout that is posted on Blackboard, this one is incorrectly marked. There it says the answer is E. I worked the problem in reverse. I did which was most soluble. So now I'll show you why the answer choice, which is correct, which is actually B, is actually the least soluble. It's for the same basic reason that E is the most soluble. So the typical thing to think about when you're seeing if something is soluble or not in a given solvent is like dissolves like. So that means things with similar properties, things like intermolecular forces, are going to dissolve other similar chemicals. So water, we know, is H2O. looks like that. It's going to be able to dissolve other things that look like that. So methanol, for example, ethanol, those are all soluble in water. E is going to be soluble in water. It also has 2 OH groups. We're looking for something that's going to be very nonpolar because water is a very polar molecule. It also is capable of hydrogen bonding, which is one of the stronger intermolecular forces. So it has 2 H bond donors, the OH bonds. It also has 2 H bond acceptors as the lone pairs. So it's going to be highly capable of hydrogen bonding. That's what gives water its high boiling point. It's hydrogen bonding with itself. If we look at the numbers of donors and acceptors of the rest of these molecules, each of these oxygens will have 2, so there'll be 4 acceptors, no donors there. None of either for pentane. We have 1 donor and 2 hydrogen bond acceptors. Here we have 2 acceptors, no donors. Here we have 4 acceptors and 2 donors. So on the walkthrough guide posted on Blackboard, this was selected as the correct answer. This is actually the most soluble in water. We're looking for the one that is the least soluble. So the one that is the greatest mismatch of intermolecular forces, the most dominant here being hydrogen bonding. So this one has no hydrogen bond acceptors. It has no hydrogen bond donors. This is a completely nonpolar. So this is only going to be able to interact with water through induced dipole interactions, which is the lowest ranked of the intermolecular forces. So pentane, which is what this molecule is going to be the least soluble in water, whereas this one here would be the most soluble. So our answer here is B. That is the least soluble in water due to the mismatch of molecular properties. This is nonpolar, and water is highly polar. Number 32, shown below is the unit cell for aluminum. How many atoms of aluminum are in one unit cell? So here we have drawn a face-centered cubic unit cell. So we have 1/8 of an atom on each corner. There are 8 corners, and we have half an atom on each face. So there's 6 faces on our cube, so 1/8 times 8 is equal to 1, so that's for the corners. This is for the faces. 1/2 times 6 is equal to 3. 1 plus 3 is equal to 4, so there should be 4 aluminum atoms. That matches with answer choice A here. So 32. Aluminum has 4 atoms in the unit cell drawn here. (33) The unit cell of crystalline calcium contains 4 atoms, so that's going to be a face-centered cubic. As we saw in the previous problem, this face-centered cubic also had 4 atoms that we calculated. So this crystalline calcium is also going to be a face-centered cubic. The radius of calcium is 197 picometers. What is the density of calcium? So here we need to first calculate the volume of the cube. So to help us do this, we can look at the useful information sheet where it shows each of the various types of unit cell structures. Here is the face-centered cubic, so we can take some information from here in order to help us calculate what the volume of our unit cell is going to be. So we're given the radius of calcium. Here we see that this diagonal along the faces is going to be 4R. So if you have your corner atom, your one in the face, and then your second corner, should be 1, 2, 3, 4 R. And then we have the other sides of that face. So this will be A, this will be B. Let's make this C here. So using Pythagorean theorem, A squared plus B squared is equal to C squared, where here A and B are equal, so A squared plus A squared is equal to C squared. And so that gives us 2A squared equal to C squared. So if we take the square root of each side to solve just for C, that gives us root 2A is equal to C. We know that C is equal to 4R. There's 4 radii along that diagonal, so that gives us 2A squared equal to 4R. We want to solve for A here, so A equal to 4R over the square root of 2. R we're given as the radius of calcium, 197 picometers. So A is equal to 4 times 197 over the square root of 2. So that is going to give us that A is equal to 557.28 picometers. So that is the length of A. We want to solve for the density of calcium, so we need the volume of our unit cell, but we're going to need that in centimeters cubed, so we can convert picometers to centimeters. So if you have 557.28 picometers, you can divide by 1 times 10 to the 10th, and that is for picometers per centimeter. That will give us that we have 5.5728 times 10 to the negative 8th centimeters. So we have the length of one of the edges of the cube in centimeters, so that is 5.5728 times 10 to the negative 8th centimeters. If we take that to the third power, that will give us the volume of the cube, which is going to equal 1.73 times 10 to the negative 22nd cubic centimeters. So that is our volume. So we have our cubic centimeters. We need to now calculate the mass of one of our unit cells. So to do this, we can look at the atomic mass of calcium. So here it's 40.08. That's in atomic mass units, so that's for a single calcium atom. So we can convert that into kilograms. If we look at our equation sheet, we have the unit conversion here for AMU to kilograms. So if we multiply 40.08 times the conversion factor, 1.66054, times 10 to the negative 27 kilograms over AMU, that is going to give us 6.65 times 10 to the negative 26 kilograms. We want grams, so we'll multiply that by 1,000. 6.65 times 10 to the negative 23rd grams. So that is for a single calcium atom. Remember that there are 4 calcium atoms in our unit cell. So we can either multiply this by 4 or divide this by our volume and then multiply that by 4. So if we divide this number by the volume, so 6.65 times 10 to the negative 23rd grams divided by 5.5728 times 10 to the negative, oh, no, sorry, that's the length. We want the volume. So 6.65 times 10 to the negative 23rd grams divided by 1.73 times 10 to the negative 22nd cubic centimeters. That is going to give us 0.3847 grams per cubic centimeter, which we see is answer choice A, but remember we need to multiply that by 4 because there are 4 calcium atoms, so that gives us 1.54 grams per cubic centimeter, which matches with choice D here. So D, 1.54 grams per cubic centimeter, is the correct answer for 33. In the lattice structures of sodium chloride and zinc sulfide, which is the correct description of the locations of the cations within each lattice? So each of these structures were shown in the PowerPoint slides from the lectures. It may also be helpful to know which types of ions match with which types of holes. So here, the ionic radius of the cations, which are what we're concerned with, the ionic radius, zinc 2+ is smaller than sodium 1+. It has less electrons, so it's going to be a smaller ion. Then if we think about the hole size, so tetrahedral will be smaller than octahedral, which is smaller than cubic. So you can gauge what the hole size is going to be based on the number of vertices that the shape has. So tetrahedral is 3 triangles with adjoining edges. There are 4 vertices there. An octahedron is 2 4-sided pyramids, so it'll have 1 vertice on top and bottom, 4 around the middle, so there are 6 corners there, and a cube. We all know what that one looks like. It has 8 corners. So this is also equivalent to the coordination number. So tetrahedral holes are going to be the smallest, octahedral will be in the middle, cubic will be the largest. So there's a few of these that we can rule out. The larger ion is not going to be in a smaller hole than the smaller ion. So sodium in a tetrahedral hole, zinc in an octahedral hole. The tetrahedral hole is the smallest, but sodium is large, so we can rule that one out. Sodium in a cubic hole, zinc in an octahedral hole, so a cubic hole is larger than an octahedral hole, so that one does match. Sodium in a tetrahedral hole, zinc in a cubic hole, so a tetrahedral hole is smaller, sodium is larger, so that one we can rule out. Sodium in an octahedral hole, zinc in a cubic hole, octahedral is smaller than cubic, but sodium is larger, so we can rule that one out as well. So we're left with these two choices. The larger ion is in the larger hole in each of these cases, so sodium is larger than zinc, octahedral is larger than tetrahedral, and cubic is larger than octahedral based on our analysis that we did over here. So the best way to decide between these two would really be to think about what the structures look like for each of these. So if you remember the sodium chloride structure, it has chlorines on each of the corners and in the face. So this is one face, so maybe it'd be better to draw it like this. Those are the face view of the chlorine ions in sodium chloride, and then the sodiums are along each edge here. So if we think about what the coordination number of these sodiums versus these chlorines is going to be, each sodium is going to have 1, 2 chlorines on the left and the right side. It'll have 1 on the bottom, 1 in the front, 1 on top, and then 1 behind it. So looking at the sodium from this side, it'll have 1, 2 chlorines, and then if we look from that side, it'll have 1 on top, 1 on the right, 1 on bottom, and 1 on left. So the coordination number of that sodium there is going to be 6. That matches with octahedral. So our answer here is going to be B. Sodium is in an octahedral hole, zinc in a tetrahedral hole. We don't need to solve for this one because we know that sodium goes into an octahedral hole because its coordination number is 6 in our sodium chloride lattice here. In a face-centered cubic unit cell, what is the coordination number for each atom? So if we have our face-centered cubic, which we have here, we can think of, let's say, this front face atom. We're going to have 1 on each of the corners. This is what the side view of the face-centered cubic looks like. So if we look from this direction, we'll see we have the central atom here with these each represent 2 atoms because now we're looking at it from this side. So 1, 2, 1, 2. So there's 4 atoms in the layer that is in the plane with the face atom. Then we also have the atoms that would be on this face, on this face, on this face, and on the right face. So the top, left, bottom, and right faces behind this atom. So here, here, behind this one again, and down here. That is going to be another set of 4, and we'll have that on each side. So above, to the right, behind, and to the left. So there's 4, 4, and 4. That is going to give us 12. So the coordination number for each of these atoms is going to be D. That is 12. For a single element lattice, which of the following have the best and worst packing efficiency? So you have 3 options: simple cubic, you have body-centered cubic, and face-centered cubic. So if you remember, for each of these, you've been given previously in lecture a rough estimate of the packing efficiency. So simple cubic is about 52%, body-centered cubic 68%, and face-centered cubic is 74%. So you can get each of these percentages by calculating the volume of the atoms within the cell and dividing that by the volume of the entire cell. So if you are interested in knowing how to do that, take a look at the week 16 Partay packet. There's a problem in there where I go through that step by step. But you can take the volume of the atoms, divide it by the volume of the unit cell. That will give you each of these percentages. So we know that simple cubic is the worst, face-centered cubic is the best, so we're looking for something that matches with that. So here the worst is simple cubic, the best is face-centered cubic, so B is going to be our answer here. Face-centered cubic is best, simple cubic is worst, and that's based on these percentages here. Number 37, which of these statements about ionic crystal structures is false? Anions usually form the lattice because they are typically larger than cations. Cations are typically smaller than their neutral atom since the electrons are more tightly held. Large cations, as defined by the ratio rules, typically occupy tetrahedral holes. Medium cations, as defined by the radius ratio rules, typically occupy octahedral holes. So as we talked about hole size earlier, we said that tetrahedral is going to be smaller than octahedral, which is smaller than cubic. And also, in reference to the ions, a cation is going to be smaller than a neutral atom, which will be smaller than an anion. So an anion has the most electrons, it'll be the largest, and a cation is positively charged, so it's going to be the smallest. So going through these, anions are typically larger than cations, and they do usually form the lattice, so that is correct. Cations are typically smaller than their neutral atom, which is true since their electrons are more tightly held. That is correct. Large cations typically occupy tetrahedral holes. So when you're talking about the radius ratio rules, there are small, medium, and large cations. Since tetrahedral holes are the smallest, it would not make sense that large cations would occupy the smallest holes. So that one is out. Medium cations typically occupy octahedral holes. Medium cations, octahedral is the medium-sized of the 3 holes. So that one is also correct. So our answer here, 37, C is false. Large cations do not typically occupy octahedral holes. Tetrahedral holes, sorry. Number 38. Iridium 4 oxide has a unit cell with 4 oxygen atoms on the faces and 2 at positions inside the cell. Iridium atoms are on all corners and 1 iridium atom is inside the cell. What is the empirical formula for the described iridium 4 oxide unit cell. So if we have 4 oxygen atoms on the faces, so 4 on the faces, so that'll be half an atom, and then 2 at positions inside the cell, so that'll be full atoms, so 4 times 1/2 is equal to 2, plus 2 times 1 is 2, so 2 plus 2 is equal to 4 oxygens. So already we can eliminate all of the answers except for B here. All the rest do not have 4 oxygen atoms, but if we look at the iridium atoms, we have 1 on each corner, so each corner is an eighth, times 8, that's going to be equal to 1, and 1 inside the cell. So 1 plus 1 is equal to 2 iridium atoms. So our formula should be IR2O4. That's what we have for choice B. So B, IR2O4, is the correct answer there. Number 39. Infrared LEDs used in television and other remote controls are commonly made of the semiconductor indium gallium arsenide, which has a band gap of 0.75 electron volts. What wavelength of light is emitted by the LED? So for this problem, we want to go to our equation sheet, and we want to use this equation down here, that the energy is equal to 1240 electron volt nanometers over lambda. So we'll write that here. So the 1240 electron volt nanometers is a constant of this equation, and we're given that the band gap is 0.75 electron volts, and we want to know the wavelength, so we're solving for lambda. So if we multiply this side times lambda and divide this side by E, we'll do the same on the other side as well. So we'll invert E and lambda. So that'll give us that lambda is equal to 1240 electron volt nanometers over E. E we know is 0.75. So 1240 divided by 0.75 is going to be equal to 1653.3, and that it will be nanometers. Here we have electron volts. The 1240 is electron volt nanometers, so the electron volts cancel, leaving us with nanometers. So D here, 1653 nanometers, is the wavelength of light emitted by that particular LED. Alright, the final problem, number 40, which of the following would form a p-type semiconductor? So there are going to be 2 types of semiconductors. There are going to be p-type and s-type. So typically you'll have an atom in the 4A group. That'll be one of the components of the semiconductor, and that will be things like carbon, silicon, germanium. So that will be one component of the semiconductor, and then the second component will typically be something either in the 3A or in your 5A group. So in the 3A, something like boron, aluminum, gallium, or from 5A, nitrogen, phosphorus, arsenic. So this will always be one component, and then depending upon if your second component is from 3A or from 5A, you'll have a N-type or a P-type. So 5A has more electrons than the 4A. So that will be your N-type, N for negative. These have more electrons, so they're more negative. And 3A will be your P-type. 3A elements have less electrons than 4A, so those will be positive relative to the 4A. So you find your 4A component, so silicon, silicon, and germanium in each case. And then which will form a P-type semiconductor, so that's going to be something from 3A. So boron, aluminum, gallium. So here we have arsenic, which is 5A. So this will be N-type. Nitrogen is also from 5A, so that will be N-type. And here we have aluminum, that is from 3A, so that'll be P-type. So of these three, number 3I here was the only one that's a P-type semiconductor, and that is going to be answer choice E. So that concludes the review of the spring 2018 final exam. So just as another reminder, the exam you'll be taking starts on May 6th at 9 a.m. goes until May 7th at 9 a.m. So you have your 24-hour window. You'll have 2 hours to take the exam, which is going to be 30 questions. So good luck.